Hello everybody, we're Alice, Larry, and Peyton. In today's presentation, we are going to be learning about non-Euclidean geometry. What is non-Euclidean geometry? It's geometry that consists of postulates that disagree from Euclid's postulates, specifically the postulate stating that one line can be drawn through a given point parallel to a given line, which we will discuss later. Additionally, there are two types of non-Euclidean geometry, known as spherical and hyperbolic. Before we delve into non-Euclidean geometry more deeply, we first need to review Euclid's postulates.
There were 5 postulates that really started geometry, and they were created by Euclid. And hopefully you guys remember some of them from freshman year, but they are that a straight line segment can be drawn by joining any 2 points. Any straight line segment can be extended indefinitely into a straight line. Given any straight line segment, a circle can be drawn having the segment as the radius and one endpoint as the center. All right angles are congruent. And finally, if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, then the 2 lines inevitably must intersect each other on that side if extended far enough. This postulate is equivalent to what is known as the parallel postulate.
In geometry, the Euclidean plane, also known as flat space, is a two-dimensional surface that extends indefinitely. Our fundamental understanding of geometry, trigonometry, and graphing is founded upon the mathematics performed in the plane. For example, the sum of the angles in a triangle is 180 degrees. Parallel lines remain parallel. The straightest possible path from one distance to another is a straight line, and the circumference of a circle can be calculated with the equation c equals 2 pi r. However, in non-Euclidean geometry, the basic examples will differ.
Non-Euclidean geometry can be broken down into many different subgroups, and one of those subgroups is spherical geometry, first proposed by the mathematician Riemann. In both cases, space curves inward, so all lines will meet. In spherical geometry, lines meet twice at the antinodal points, and in elliptic geometry, lines only meet once. A line is represented by the shortest distance between 2 points on the surface of a 3D sphere. In the case of a straight line, it will encircle the sphere and have a distance of 2 pi r, the same thing as the diameter. And even though the sphere is visualized in 3D, it actually exists in 2D non-Euclidean space. So when any 2 lines intersect twice, the intersections are called antinodal points and are on opposite sides of the sphere. Using this information, we can move shapes on a 3D surface of a sphere because there's a one-to-one equivalence between the rotation. This usually applies to a shape rather than a point, as we must be able to specifically rotate certain theta degrees in the spherical plane, as well as have latitude and longitude.
Like all other non-Euclidean geometries, the hyperbolic plane is established by amending one of Euclid's postulates, specifically his 5th postulate regarding parallel lines. The modified version of the parallel postulate for the hyperbolic plane states, given a line L and a point P not on that line, there is more than one non-identical line through the point P and not intersecting L. As a result, the hyperbolic plane is a plane where space curves away from itself at every point. To put it in perspective, the area around each point in the hyperbolic plane has the shape of a saddle. As many people have found working with the hyperbolic plane difficult, the Poincare disk model was created to be a model of the hyperbolic plane on 2 dimensions. The Poincare disk model can be thought of as a circle, but badly distorted at the edge. Objects near the edge of a Poincare disk are larger than they appear. The outline of a disk does not actually occur in hyperbolic space. Rather, it is an arbitrary line that helps geometers work with the plane. In the hyperbolic plane, geodesics play the role of straight lines. On the disk model, geodesics are arcs of circles which meet the edge of the disk at 90 degrees. Arcs that do not meet represent parallel lines in hyperbolic space, and arcs that meet orthogonally represent perpendicular lines. Unlike Euclidean geometry, in hyperbolic geometry, there is no line that remains equidistant from another line. Instead, the points that all have the same orthogonal distance from a line lie on a curve called the hypercycle. Another interesting curve in non-Euclidean geometry is the horocycle, which is a curve that has normals that converge asymptotically in the same direction. In hyperbolic geometry, the sum of the angles in a triangle is equal to 180 degrees minus the defect. The area of a hyperbolic polygon is equal to pi divided by 180 times the defect. Ideal polygons have all their geodesics meet the edge of a Poincare disk. The points on the edge are called the ideal vertices, and each have an angle measure of 0, as the edges are all perpendicular to the edge of the disk. The area of any ideal polygon is thus the number of sides of the polygon minus 2 times pi, as the angle measures at the ideal vertices are all 0, thus making the defect 100.
Here's an example of a Euclidean proof. So given a line L, you must construct a triangle with one side on L such that the sum of the angles is 270 degrees. So first you must construct a perpendicular segment with length q from line L to the pole. Then define two segments with a distance of q beginning at point A and ending at points B and C respectively. Then connect points B and C to construct the last side of the triangle, meaning that BC must be the length of q because point C is the pole for AB. Finally, all segments have length q and go through their respective poles. Thus, they are perpendicular to their respective line and create a 270-degree triangle.
Euclid's fifth postulate states that if the sum of the angles alpha and beta are less than 180 degrees, then two lines, produced indefinitely, meet on that side. Essentially, this means that if alpha and beta add up to 180 degrees, lines 1 and 2 are parallel. Many alternative formulations to this postulate were created to provide a simpler explanation. One reformulation, stated by Playfair, a mathematician, was, through any given point can be drawn exactly one straight line parallel to a given line. To disprove Euclid's postulate, an alternative postulate called five none was created. Five none was defined as, through any given point, no straight lines can be drawn parallel to a given line. If the alternative postulate could be proved, then the reformulation could be disproved. Thus, Euclid's fifth postulate could be disproved. The process of proving five none can be best illustrated in these step-by-step diagrams. First, choose any straight line in Euclidean space with 2 points A and B on it. Draw lines through these points and perpendicular to the straight line. The five none postulate suggests that these perpendicular lines, if projected, will eventually meet at some point, which we will call O. We can infer that lines AO and BO are the same length and create a symmetrical figure. AO and BO are considered straight lines because this is a non-Euclidean geometry. Next, find the midpoint of AB and call it Q. Then draw a line perpendicular to AB at Q. The perpendicular must pass through O because if passed on either side of point O, the figure will not be symmetrical. It turns out OA and OQ are the same length. To picture this, consider the triangle OAQ, which is constructed the same way as triangle OAB, with two perpendiculars that are projected until they meet. Thus, triangle OAQ has the same symmetries as in triangle OAB, so OA is equal to OQ. This reasoning can be applied to triangle OBQ, so OB is also equal to OQ. After repeating this construction multiple times, we can extend the figure to have multiple right angles. Eventually, these straight lines will fill all the space, and the space will wrap back onto itself in every direction.
The most famous artist who worked with non-Euclidean geometry is M.C. Escher, who's famous for his works tessellating the hyperbolic plane. A hyperbolic tessellation is a covering of hyperbolic space by tiles, with no overlapping tiles and no gaps. The Schläfli symbol, denoted by n, k, describes the regular tessellation by n-gons, where k meet at each vertex. There are infinitely many regular tessellations of the hyperbolic plane. You can determine whether n, k is a tessellation of the Euclidean plane, the hyperbolic plane, or the elliptic plane by looking at the sum of 1 over n plus 1 over k. If the sum equals 1/2, then n, k is a Euclidean tessellation. If the sum is less than 1/2, then it is a hyperbolic tessellation, and if it is greater than 1/2, then it is an elliptic tessellation. Escher's circle limit 3 is his most accomplished print based on hyperbolic space. It is also his most subtle. Looking at the white spines of the fish, it appears to be a tessellation of hyperbolic space by triangles and squares, with 3 triangles and 3 squares coming together at each vertex. This would mean that the corner angles of both polygons are 60 degrees each. But this gives the triangle an angle sum of 180 degrees, which cannot happen in hyperbolic space. Another interpretation of the circle limit 3 is the 8-3 tessellation by octagons. Drawing hyperbolic tessellation by hand is quite difficult. However, tessellations by ideal polygons are somewhat easier to deal with. The advantage of an ideal tessellation is that all vertices lie on the boundary of the Poincare disk. Since the tiles in ideal tessellations are not polygons but ideal polygons, they do not have Schläfli symbols. However, they do fit into the scheme of regular tessellations, with the odd feature that infinitely many tiles now meet in an ideal vertex.
Saccheri was another mathematician who really enjoyed playing around in geometry. He tried to approach the parallel proof by solving it indirectly, so he assumed that the parallel postulate was false. He said that given a quadrilateral ABCD, he could prove that AD equals BC and angles A and B were right angles and angles C and D would be equal. He then came up with 3 different possibilities, where C equals D and they're both 90 degrees, where C is equal to D and they're both greater than 90 degrees, and C equals D and they're both less than 90 degrees. Saccheri was able to prove that the hypotenuse of an obtuse angle leads to a contradiction, but he was unable to disprove the acute angle. This led to the non-Euclidean theorem that the sum of angles in a triangle is less than 180 degrees.
Some applications of non-Euclidean geometry include gravitational lensing, which will be discussed shortly, plane travel, as non-Euclidean geometry shapes spherical Earth in such a way that some places like Florida, Alaska, and the Philippines are in collinear locations in spherical geometry. Time-space continuum, which combines the ideas of time and space into a 4-dimensional continuum, in Einstein's famous theory of general relativity.
One of the major fields within non-Euclidean geometry is Riemannian geometry, which focuses on the study of curved surfaces. A fundamental concept of Riemannian geometry is the minimal geodesic, the shortest curve for any 2 points on a curved surface. On Euclidean flat surfaces, there exists only one shortest segment between the 2 points. On curved surfaces, however, there can be an infinite number of minimal geodesics, such as the infinite number of minimal geodesics between the north and south poles of our Earth. An important tool used to measure how much a surface curves is the sectional curvature. This value can be calculated using the second partial derivative of the function used to describe the surface. To study the sectional curvature of the given point, you need to find the tangent plane of the surface at that point. Riemannian geometers used previously described techniques to study higher dimensional spaces such as our universe. While from our vantage point space looks like it's just a 3-dimensional Euclidean space, space is actually curved and bent near heavy stars and black holes. Thus, there are pairs of points in the universe which have more than one minimal geodesics between them. Astronomers use these points in a technique called gravitational lensing. Gravitational lensing is based on the theory that mass curves the space around it, and the light will then travel along the curvature of space and time. The main use of gravitational lensing is to help us see farther into our universe. It is used as a magnifying glass for distant objects, as light from distant objects can be deflected in our direction, making them appear brighter and larger. This allows us to peer deeper into our universe, detect planets, and observe invisible objects such as dark matter. The amount of space that is curved can be estimated using theorems from Riemannian geometry, and measurements taken by astronomers. Physicists believe that the curvature of space is related to the gravitational field of a star according to the partial differential equation called Einstein's equation.